Well, now we have our, well, we need to do our full transmission line.
But we have
we're
a
going to start
lossless.
with the lossless one.
Right.
Yep.
So I guess we know already from KVL for the lossless line that dV dz is equal to minus L di dt. And I've left a big blank here because we're going to fill in the blank. And the other equation is for KCL di dz is equal to minus C dV by dt. So we're going to fill in some blanks here.
Okay.
But before we do that, let's have a picture of what we expect to see in a full transmission line model.
Well, it's pretty obvious in any conductor, you would have some sort of resistance inside. So what if we just add some series resistance
Well,
here?
let's put that in to start
that
with,
in.
see if that's complete or not. So while we're doing that, the L also can have losses in setting up magnetic fields, friction losses in the inductors. Oh, so we should put in values for these little pieces.
You're right.
It's going to be the same as before, a little piece of resistance. Oh, it looks like we're done.
Yeah, I guess we're done. We can go have lunch.
No,
Very good
but
thing.
what about this guy?
What
The
about that guy?
capacitor. Like,
What happens to that
well,
guy?
is a capacitor two plates and a dielectric and just the storage of charge? What else can happen in a capacitor?
That's all I know about capacitors. Are you saying there's more to this?
Well, sure, we could have like capacitor, and here we have dielectric, and so we have charges on the top and charges on the bottom and an electric field, but surely there must be something else going on in the dielectric.
Oh, you mean there might be some sort of loss in there?
Well, there's loss in the dielectric setting up the little dipoles, but there's also shunt currents. In other words, this can have some conductance.
Okay,
And so we
okay.
have to account for that as well. So we
Okay,
have
let's
to
do
do
that.
something.
I guess we just add resistance on the side of this.
Okay, and when we come to model it, this is in parallel with that. So this models a shunt resistor, but we don't want to stick it as a resistor.
Oh, then we just put a conductance next
Yeah,
to this, so we
put
can just add them together.
Yeah, we'll just put
Okay.
conductance in, so we can just add them. So this is the conductance current leaking through, and this is the charging current through the cap, and they just add. We don't have any reciprocals of things to put in. So
Okay.
that's the model.
Great.
So now we can take a big leap and say, well, look, we have these inductor pieces, L di dt, but through the resistive pieces, just the straight current. And so we can modify this by just adding the extra bits, which is going to be I, R, plus L di dt.
Looks
and,
good.
and then the shunt currents add too. So we're going to have the C dV dt current plus GV.
So if we put a resistance here instead of conductance, then you would have divisions instead.
Yeah, we'd have 1 over some R. for
What's
the
cleaner?
This is way cleaner. It has a nice symmetry to it. And now these are the full equations for our transmission line and what
Wow.
we're going to model.
Easy peasy.
Well, easy peasy, but not so easy now to solve these equations.
Oh.
Much harder.
Clearly, it's a work for them, not us.
Well, we will guide everybody along as to how we can solve these equations. Good job.
Sounds great.
We now have full transmission line models for you to play with.
Very great toy.